Hi there. In this video, we'll go through another example of a theoretical hypothesis test for a proportion. Okay, and this example will probably look familiar to you. I hope it looks familiar because we did this with randomization before. Okay, so let's do it theoretically, and then we'll return to randomization as well. So a company develops what it hopes will be better instructions for its customers to set up their smartphones. The goal is to have 96% of its customers succeed. The company tests the new system with 400 people, of whom 376 were successful. Is this strong evidence that the new system fails to meet the company goal at the 5% significance level? Okay, so, and I've got my steps handy right here. I'm not going to write out the A, B, C, D, E this time. I'm just going to kind of go through the steps. And we've done a couple of these already, so feel free to try this on your own. Pause the video, try it, and try it kind of in steps and then catch up with me, or try it all on your own. Whatever, it's up to you. That's the beauty of video. Okay, so let's first write out our hypotheses, our H null and our HA. Okay, so I can write that out without even really thinking about it because I know it's H naught colon P equals and HA colon P something, right? Okay, so let's see what information we have. The goal is 96%, okay? So that tells me that is like the sort of like status quo. And then we have a sample as well. So we have 376 over 400. So that's our p hat, whichever's coming from data. It can be tricky to distinguish between these two things. That's why we're doing this example for the theoretical. So I know the p hat is 376 out of 400. And we can calculate what that is. 376 divided by 400 is 0.94. You probably remember that from the last time we did this. Okay, so I know that's my p hat, so the other one has to be p0, okay, if you're not sure. 0.96. I know it's worded a little differently, like it almost sounds like that's the claim, but let's read what we're supposed to test. Is this strong evidence that the new system fails to meet the goal at the 5% significance level? Okay, so that tells me that the claim is that they're failing to meet the goal. So is P less than 0.96? So it might have been easier if I wrote less than 0.96 first, and then I would know that the alternate, or the null, is equal to 0.96. Okay, so this is a left tail test, because failing to meet their goal means we're testing, is it significantly less than? We know it's less than, we just don't know if that's due to chance, due to sample variation, or is it significantly less than 96%? Okay, so we've got our hypotheses written out. The next thing is to check the conditions. Okay, and I'll do the quick version here because we've been writing these out a lot. So independence. Each customer needs to be independent of each other in their ability, both tech ability and ability to follow directions, I would say. And then we need a random sample. Okay, large population. We need our population to be greater than or equal to, add a 0 on there, 4,000. Okay, population has to be 10 times our sample. So I would say there's safely more than 4,000 people who use smartphones in the United States, or even those who might use instructions to set up their smartphone. Greater than 4,000. Okay, last thing, success failure. NP and NQ. So N, and remember it's NP naught. So 400 is our total times 0.96. And NQ naught It's 400 times, this one I can do in my head, 0.04. You can write it out 1 minus 0.96 if you want to. Okay, 400 times 0.96. This one is over on the extreme, so we need to check this for sure. But this is not the one we'd be concerned about, right? It's the low one. So let's check 400 times 0.04. Okay, 16. So we barely made it. Not barely, but we made it. 384 and 16. Those are both greater than or equal to 10. Okay, so I'll put a check. Check, however you want to do it. Okay, conditions check. This seems reasonable. Okay, remember this is the part we would all, except for the p hat, everything else we would be doing before our test, before we collect the data. And so we need to know our sample size to do that. Okay, so next is to calculate our test statistic. Okay, so that is a z-score, right? Z is equal to, got my formula that I'm looking at over here, p hat minus p naught over the standard error, which is the square root, p naught, q naught over n. And remember, we're setting up the hypothesis test assuming the null is true. So that's why we're using p naught in everything, our conditions and our standard error and our mean. Okay, so our p hat was 0.94 minus 0.96 over square root 0.96 times 0.04, because I already calculated my q naught, or I could do 1 minus 0.96 over 400. Okay, so this is going to tell us how unusual is this value, right? How many standard deviations away from the mean is it? Okay, so 0.94 minus 0.96 is negative 0.02. We expect a negative value if it's a left tail test, right? We should be below the mean if it's a left tail, otherwise we're way off. Okay, so we got a negative. Now I'm going to divide that difference by the square root of 0.96 times 0.04 divided by 400. Negative 2.04. Standard deviations. And for my p-value, you might want to be a little bit more exact. I should have written negative 2.0412. So I'll write that down below here. 0412. Okay. Now, if I'm recalling correctly, I feel like this wasn't significant last time we did it. So let's see, okay? This is where, now that we have our test statistic, do you know what the next step is? We got to find our p-value, right? So our p-value is the probability of getting this if the null is true. Probability that z, it's a left tail test, so we're going to go less than negative 2.0412. Okay, it's a one-tail test, so we just have one direction to go with here. Okay, let's see, let me go to my normal distribution. I think I was on another, we're doing our last question there. So let me just clear it out, go back to Staplet homepage and back to our Staplet normal app. Okay, a p-value is an area, it's a probability, so we're going to keep with the first option under operation. And then we have a z-score, so that's 0, 1, mean and standard deviation. Plot our distribution, and then for a left tail test, we're going to select to the left of a value and put in our value. Negative 2.0412. Negative 2.0412. We can see how much difference it would make. You can play around with it and see if that last two digits make much difference. Okay, so our p-value is 0.0206. Okay, so that actually is significant. So we may have come up with a different conclusion. I'll have to go back and check. 0.0206, or maybe it was significant the whole time. I just can't remember. So our p-value is small, right? So that means that getting this result of 376 out of 400 to be successful, that actually is pretty unusual if the null is true. Okay, so it does look like they failed to meet their goal. Their goal or we're testing a claim that's kind of a negative claim, right? That they failed to meet their goal. So it is significant, but that's kind of bad for them. Okay, so this is a significant test. Let me go back to the note. So I wrote the p-value, and you can see, just to double check, your z-score on the graph, and the area is 0.0206. So that's our p-value. Now I'm going back to the notes. I wrote down our p-value. That is less than 0.05. So this is significant. Oh yeah, I think it was a different one that was not significant last time in our randomization examples. I'm thinking back to that. Okay, think about what the next step is. While I check what it is as well. Okay, so that was D, right? So we just compared the p-value with the significance level and whether the result is statistically significant. Okay, we're up to our conclusion. Okay, so with a p-value of 0.0206, we could say this is strong evidence. It's pretty strong, right? It's only 2%. Actually, I want to say we reject the null first. Then I'll talk about the evidence. We reject the null hypothesis. And there is strong evidence that the company, and I'm going just right back up to the claim here, what we're testing, that the new system fails to meet the company goal. Okay, so let's see evidence that I'm going to change this to new system, that the new system fails to meet the company goal. Okay, great. So that is our hypothesis test. And remember how we talked about statistical significance versus practical significance? So they still had a 94% success rate, right? So that's pretty good. I wouldn't overlook that. So it's like, is that 2% practically significant? However, there's always always room for improvement, though. So they could keep improving their instructions and then keep trying to get that 96% goal. Okay, let's double check our stat key really quick. I want to do the randomization. So here's the stat key homepage, and our randomization tests are the right column. We are doing a single proportion here. I'm going to go single proportion. We got to put in our null was 0.96. And then we need to put in we need the sample size for this. So we need to put in our 376 out of 400. I almost just thought about putting in 94 out of 100 because that's what it reduces to. But that wouldn't be the same, would it? And you could test this out. And the results might come out the same or not, but remember that difference in sample size of 100 versus 400 would change the standard error quite a bit. So just an interesting little thought I had. Okay, I'm just going to go right to the 2,000 samples because you've done this a bunch. And then we would click on left tail. And it just so happened, so remember this always comes up, the left or the tail probability as 0.025 because that corresponds with 95% in the middle. It just so happens that corresponds to 0.940 0, usually you have to type that in. I'll just do it anyway for fun. And okay, so it was somewhere in 0.94, but it wasn't quite exact. So I think there is benefit in actually typing it in again. That was kind of my question why I did that. So I put in the 0.94. I put in our p hat along the horizontal axis, and that's now giving us a left tail probability of 0.029. Okay, so it's not too far off. I'm just going to make a note. Randomization. Okay, I'm going to show you the note I made. I just wrote the randomization p-value is 0.029. I'll just put it in brackets for comparison. I don't know if there's one R or two R's in comparison. You can check me. Okay, great. So those two would agree. That's good. Now let's do our 95% confidence interval and see if those agree. Okay, so first I'm going to write out the formula again. P hat plus or minus Z star times the square root of P hat Q hat over N. Okay, remember these agree sometimes and sometimes not. They use different values for the standard error, right? This one uses P hat and our hypothesis test uses P naught. So depending on how far away those are, could affect our results. Okay, so for our P hat, we have 0.94 plus or minus. It does say 95% confidence interval, so 1.96 times the square root of 0.94 times 0.06 this time over 400. So I did the 1 minus 94 in my head, 1 minus 0.94. So this will be 0.94 plus or minus, and we need to calculate our margin of error here. I'm going to do the whole margin of error, 1.96 standard errors. So 1.96 times the square root, 0.94 times 0.06 divided by 400. And that is 0.0232, and there's a 7, so 0.233. Okay. Now we can go ahead and subtract and add. I think I'll write this over. I'll go over to the right and do that up here. So let's do 0.94 minus 0.0233. Enter 0.94 plus, plus 0.0233. Okay, 0.9167 to 0.9633. 0.9167 to 0.9633. Okay, now remember what we're looking for when we compare our confidence interval with the hypothesis test? We're looking to see what's our null value again. We're looking to see whether our null is in the interval or not. Okay, and if it's a two-tail test, it's either in or out, right? But I'll talk about how you might do this on a one-sided test. Okay, so we're looking for 0.96. Is that in our interval or not? I'm just going to mark where that would be. So that would be, it's closer to the top. It's kind of close to the top, right? 0.96, that's our null value. So it's in. So that actually supports the null hypothesis. Interesting. So it is kind of close though, because it's kind of on the edge, right? It's right 0.9633. So what we're saying is the plausible values for, given this p hat, the plausible values for the customers that that did succeed were about 91, almost 92%, up to just over 96%. So it is plausible that they met their goal, okay? So that's interesting. And then, so this is kind of interesting too for a one-sided test. It could be out, but the direction out that it's out would matter, right? Okay, so that's going a little bit beyond what we're going to study in our class. But just kind of keep that in mind that since we have a left tail test, if it was inside or to the right, that's going to support the null, right? Because that's going towards, oops, I'm pointing above the screen. It's going towards the null or higher, right? It's not going to the left tail. So inside or to the right supports the null. And then if we had, see if I can fit this in here, if we had a right tail test, inside the interval or to the left supports the null. Okay, because it's really in the tail. When you're small in the tail, that provides evidence against the null or for the alternate, right? So if it's away from the tail, that where you're going to fail to reject. So let's write our conclusion on this one. Here we would, if we were only looking at the confidence interval, we would actually fail to reject. So they don't agree in this case. So the confidence interval would fail to reject the null, H naught. So the methods disagree. Or so the two methods disagree in this case. Okay. I was just trying to read a little bit more about this online to see if people really do this for a one-tail test. And I actually came across an article saying that the two methods would agree all the time. So I need to make a comment or something on that article because I don't believe that's correct. Sometimes they disagree, sometimes they agree. Okay, it depends a lot on the difference between the two standard errors and other things, okay? So, of course, we could, because we're kind of doing this sort of central confidence interval with a one-tail test that would be shifted over, we could do more of a one-sided confidence interval, and then that would match our test a little bit better. So just know that that's possible. Again, that's another stats class. It goes beyond the scope of this class. So if you're interested in more of that, then you could take another stats class. Okay, great. Thanks for watching. I'll see you in the next video.